generate formally verified code. So and then for that, like it was mentioned, like we need somehow to build data that is, we know, like we can use that data to actually train these models to, well, they already generate relatively good verified code, but like to even improve their rate, their success rate, we'll need to like train the models in this view. So, well, this is just like to show that, like from the 80s, we've had problems like disasters, which are actually due to bugs in software. So, problem is that these days more and more software is like, we have even more software, like software is everywhere. So, like then definitely we will have more bugs. Like we have bugs that we know of, we have bugs that we don't know of but are exploited, and then so now at the same time, like we had the AI capabilities going, like we get better and better AI at various well-defined problems. But now, actually, recently is that AI is being used for like everything, like just coding, ChatGPT, video agents. So that might create might multiply our problems. So the question is, how can we like control this kind of AI? And so what we observe at the same time, well, the promise of AI in like doing formal stuff like reasoning and mathematical reasoning. So actually, maybe there's a promise there that we can resolve the tension, the problems of AI with AI itself, and like somehow. So we need to find a kind of framework that will put this kind of constraints on the AI. So that's like we call vericoding. Is like just AI coding with AI generated proofs. So we put the constraint. This is the specification. Give me the code, but also give me the proof, right? So. Well, we all know formal verification. This is like very good. We have no bugs within the spec, so I will not spend time. So this is just repeating like the improvements in mathematical theory improving. The problem is that most of the coding done today is still like with vibe coding. So like we want to set the stage, or like to make it more usable in practice to actually do verified coding. So for that we'll need, what do we need? Like first of all, like we have the formal verification view, but also the vericoding view, which is like you have a specification, then you want to generate the program and the proof. In both of these problems, the specification is important. So we'll need to find a way to give correct specifications to the LLM, and make humans actually understand, like write the specification, like even not human, like developers. So not only experts, like even for developers, we want to to find what is the way of writing specifications, so that it's clear for Rust developers or Dafny or like, and then program proof generation, which is like a separate task. So this is probably more like, it's still like research to do, but this is like a precise task. So that's something that we can already work with, like, because we can evaluate it. Is it correct? Is the output of the LLM correct or not? So since it's a precise task, we can actually now try to say, so the goal of this work that I'm presenting is that we are trying to accumulate this, like a big benchmark of such precise tasks. So like we have like 10,000 files that like Dafny', Verus, and Lean. And then we did experiments to see, like with various models, which is like a few months old. I think those experiments are a bit outdated, like with all the progress, but it's still interesting to see. We had good results. Now, okay, even better, but there are some problems still, like, because some of the problems might be too easy. Like they come from, we had problems with the formalizations, like some of the specs are maybe simple, so we need to maybe improve the specs. But the idea is that we looked like at a few, like all the available and not available formalizations. So like we started with some benchmarks that exist already, like Dafny bench, which was mentioned earlier. We had like some JetBrains organization had another bench in Rust. These are some benches in Lean. And then we formalized also with maybe an approach similar to what was presented in the earlier talk, this kind of apps and human eval programming problems in with LLM-based approach. Then we also formalized some parts. Actually, everything from the NumPy library, like this is like Python library. So it's like just to test to see, and there's not like it's like some array manipulation algorithm, so it's not trivial. It's interesting to see how LLM will actually, just given the specification, if the LLM can come up with that, with proofs. So this is just like a summary of our approach. So actually, for some of the things we had, for example, Dafny bench, we had 443 files in Dafny. This came in the Dafny bench, I think there are 600, but then we split them into individual tasks. It went to 800 because some files are multiple tasks per file. Then we did some cleaning. I'll present a bit about the cleaning because in Dafny bench, the quality of the bench is not great. So you need to, some of the problems are trivial. There's lots of Fibonacci problems repeated like 10 times. So we had to remove that. Part of it manually, part of it we have like some similarity algorithms but we didn't really apply. I mean, we have thought about it, but like this is still very much work in progress, how to clean up the specs. Like we have like many specs now, but like I think we need to develop the methods how to clean them up. So yeah, so this is like just a bit about the sources. This stuff maybe I'm not spend much time. So the app, so we formalized from like Python to Dafny with an LLM generator as judge in between. But then there's you're never we don't have like a formal a rigorous argument that the spec is the same. It's all like based on, we did some manual checks on the random samples, but it's like still works in progress to get better results. VApps, this is a lean set with 4,000 tasks. We didn't bother translating it because actually translation, this actually costs a lot of money to use the LLM. This is like 4,000 tasks, and then we said, okay, since they are actually still like they're relatively weak, some of them are trivial, so it's not, the value is not clear, but lean still struggles. Like we are surprised, like we'll see the results later, that results in lean is not great. So we it's one of the questions of our work is like why lean for code generation and code proofs is not as good as as we would expect, because it's good at math, but maybe not so good at code yet. So, or maybe the way we wrote the experiments, I'll show a bit. Like I think some of our lean, because we have some, like me myself, I haven't worked with lean, but we have people who have worked in the team, and they said, okay, maybe we need to pass more of the lean state or something like that to the LLM to make more like the work with the LLM look more like the human works, like in the interactive way, like to pass all that information, contextual information to the LLM is not obvious yet. How to, what's the framework for that? Then this is like for Rust. We took like some of the Rust bench. They have a model, some model of human eval, but we looked at their human eval modeling. It's still they have some tasks we could see that it's not great. So I think even for Rust we don't have yet a formalization of human eval like we have for Lean. I maybe present like the one in Lean is. Where is the Verina and I think I skipped here. So Verina and Clever, these are very good clean benches, and then we translated them to Verus and Dafny, but it's still for Lean. We have this for Lean, but we don't have it really gold standard for human eval in other languages yet. So that's part of the maybe future and ongoing work. This is a bit like NumPy. We generated them in Lean with this RECGen Hor triple style. Yeah, BigNum is interesting, and this is I hope to have time. It's I'll present some of this is a case study of the difficulty of writing the correct spec, because writing even for big maybe let me go because I'll run out of time. But what is a spec? I've been talking about tasks and LLM. What we give to the LLM? We give a context, which is basically all the formal definitions, and then we give the specifications. This is the function for which I want the code. And then the LLM will give me some implementation and helpers. So this, for Dafny, it looks like this. This is a valid bit string. This is something in addition. I want to just add two numbers, in crypto operations. These are big strings. So the challenge here, so what is the tasks is to give me the addition of two big integers, like so the addition should satisfy that when I transform them into like real integers, like the mathematical integers, like I have this translation function which tells me what is the mathematical value of my string. This is just the classic bit string decomposition. And we have this. Now, the problem with this specification is that, okay, the LLM gives us a solution. So we need to find a way to, I have 5 minutes, okay. Like to say, is this solution correct or not? Like, do we accept it? So it will satisfy, so Dafny guarantees to us that it will satisfy this. But the problem is that there is like for this particular task, there is like the shorthand that the well, not even the humans, they might use like a cheating trick here is that they might first map into the integers, the mathematical integers, perform the addition from the mathematical integers, and then map back. So they would not perform the real addition. So it's very difficult to specify like how to specify that in Dafny, or like I don't know if we have like the tools to specify this, like don't do this kind of cheating. Maybe in Lean we have some more control. So yeah, so like this is like our translation, like because we needed to translate between languages, but okay, I will not spend time. This is like a classic, like okay, we did some specification, like the filtering on specifications, like because like some part of it we did it manually, part of it with some similarity filtering and mapping of specs into this kind of vectors. And then the vericoding, in the vericoding pipeline is like we have a spec gives to the LLM that gives us some blocks. We need to first validate the blocks and then verify the file, like the Dafny or Verus, or give there or back to the LLM. So maybe this was why the problem was with Lean. Like the Lean was giving us the proof, then we were checking that proof, then you get so, and then that's only for 5 rounds, and that's not gonna work well in all cases. Yeah, so these are like the results. So we got best results with Dafny, yay. But yeah, I think this is because yeah, so we have more then we have the a bit less well with Verus, but Verus, it's causing all these problems related to big num with interaction to bit strings, and like we have executable types, real types, and like in Dafny we don't have this kind of problems. And the Verus, I must say, that's why I was saying with the compiler message, like LLM, because we give the compiler message to the LLM, but even for humans I can understand, but for LLM, so I think in general we need like the compiler messages could be better for Verus, for example. Yeah, so like we have like some speculative reasons why Dafny is better, but yeah, so like for Lean, we did some vibe coding combining, but it just doesn't add. If you add a natural description, it actually makes it worse. And yeah, then we actually, since we have many LLMs, we just take ensemble. We put them results, like some LLMs solve one problem, another solve another problem. So we put them together. Like this is like what we ensemble method here. So there is future work. Like I was saying, that we need to work on task quality, on more benches, more difficult problems, because still we have like relatively simple problems, and then to improve the performance once we have the bench. So now we have some people who are working on actually reinforcement learning and maybe getting better results from Lean, and then yeah, so that's our conclusion, is that yeah, it's something that can be done, and we can work on it. Thanks.
Any questions?
Yeah.
You mentioned that it's expensive. How much did it cost in the like? What's the ballpark?
Yeah, actually, yeah, I'm a bit embarrassed, but yes, at some point we realized, okay, wait. By this point, we spent like I think we spent at least $20,000. So on the you know, like, because we had like lots. Some of the LLMs are more expensive. Like if you had Claude and GPT and things. So yeah, so that's why but yeah, so thanks. It's interesting, yeah, because it's quite interesting that actually this costs, so we need a way to also enable like maybe people who don't have like good funding to actually run this kind of model. So I think we need to find a, I don't know, a framework that allows less cost for research. Yeah. Okay.
Any more questions?
Thank
Let's thank the speaker again.
Thanks.